Hello, folks. Happy Friday. It is Friday. Um, Good to see you all. I figured live stream of the week as we're having some fun over on Substack again. I just wanted to play around a bit more, so I'm here to talk about research and, in some ways, reinventing the way that research is delivered. So, for people who don't know, up until the turn of last year, I used to work as a contractor at NASA JPL. I've been there for about 8 years, along with a whole bunch of other stuff. But clearly, the work that I was doing at JPL was an awful lot of R&D and research-based work. Trying to not do the research, but provide ways for researchers to interact with data that is different from the usual sort of like chuck it in a spreadsheet and hope that everything sticks. Because a lot of this work is grant based, and so a lot of the work that ends up getting done is like one time pieces of work that prove out a concept, and then potentially that work is then either archived or chucked in the bin. And then a few years later, the same work comes round again, and you have the more money being spent on doing the same thing time after time. And so one of the things that I wanted to try and achieve was to save money, taxpayer money, in effect, by giving researchers the ability to create something bespoke, something that's going to fit their needs, something that's going to allow them to share their research, something that's going to allow them to accelerate their research in a way that allows them to build something that's not just a spreadsheet. Because spreadsheets serve a purpose, don't get me wrong. But as soon as a researcher gets their research into a Python notebook that's on their laptop, into a Excel spreadsheet that's on their laptop, the lineage of that data, the understanding of where that data came from, the process that it went through, the changes that's been made, the libraries it's been hacked around with, the Excel version it's been dealt with, the import, like it all goes away. And so your ability to be able to reproduce that research is almost zero. And so what we want to be able to do is create a platform that allows researchers to do their research in a collaborative environment that is a cloud-based environment that would allow them to speed that stuff up and share things amongst other researchers, allowing them to, do their job more effectively, allow them to do their job. And so we built at JPL a project called Pixlise. And I use this template a lot when I'm talking to other organizations that are interested in dealing with research, because it's like the gold standard from like open source research development. I haven't come across a better platform. I'm of course biased. There are other platforms, but like for something that we built that was like unique for that platform, Pixlise was certainly something a little bit different, a little bit special. And so I want to do a couple of things. I wanted to sort of like walk you through what the platform is. Hopefully, if I can remember how it works. It's been a while. And then also talk about some of the design decisions, the code that we, made, built, used, that type of thing. So just bear with me whilst I log back into the platform, or attempt to. So, I wish I'd teed this one up earlier. Hold on. There we go. Okay, now I should be able to share my screen. So, Pixlise was built to allow X-ray spectrometers for Mars Rover scientists to collaborate. So the Pixlise, sorry, the Pixel instrument was sponsored by the Queensland University of Technology in Queensland, Australia. And so there was clearly a distributed team. We've got people in LA, we've got people in Europe, we've got people in Australia, and they've all got access to the data. They all want to be able to understand what's going on, and they want to be able to collaborate effectively. And so we eventually convinced them that Pixlise was like the way to go. So if I don't know which one it is now, hold on. That one? No, that one. There we go. So what you can see here is the landing page of Pixlise. I'm going to take you on a whistle-stop tour of how this product works. This is public. I'm not doing anything that's like you can't go and do yourself. So if you go to pixlise.org and sign up, you can see exactly the same stuff. They've got this nice little landing zone now. I'm pretty sure if I click on this, you might even see, is the team thing still there? Oh yeah, there we go. I'm still on the list. And so, proof if you need it. But you can see also down here the amount of publications that Pixlise has been involved in. It's growing, which is cool. And an awful lot of stuff about why we built what we did. Anyway, I'll take you through the platform briefly. So if I click on the open button, I get, let's make this bigger so you can see it. I get access to some data sets and the general GUI. It tells me what version I'm using, tells me who I am, and then I can see these two data sets are available to me as Joe Public User. One of those is has got extra layers attached to it. One of them is just a standard scan. So I'm going to pick this one here. And so you can see a bunch of metadata that's over the thumbnail, sort of tells you what the rover was up to. So drive ID, Sol number. Sol is a Mars day for anyone who didn't know what Sol is. And so if I click on, they change this often. There we go. Open. And then possibly zoom back out. So that it, oh, no, that's the wrong way, isn't it? Hold on, how do I go back out? There we go. There we go. So what we have here is the sort of workspace that we built for the X-ray spectrometry scientists. And so now I've got this open. You can't see that one properly. There we go. So this will now give me, no it won't. It's supposed to give me a bigger image. There we go. I'll zoom in. So these dots here are basically where the spectrometer is scanned and some other bits and pieces because they've got the plus signs and what have you. And you can use various bits of tooling to like select the bits that you're interested in. So underneath what you can see is like the rock, and you can also see how small these scans are. So this is like 1 millimeter, 2 millimeters. It's about like, half a centimeter by half a centimeter. These are tiny, but there's lots of little zaps going on. And so you can see the bits are interesting. So there's obviously some zaps on different colored rock or has different minerals in. And so I can then use the tooling, if I can remember how, to like select the bits that are of interest to me. As an end user, as a scientist, you can then select regions of interest. If I actually select, have we got any here? User created, built-in ROIs, here we go. So like you've got all points ROI, I can tell it to select all of that. There we go. So it basically has selected all the points at this point. And then you can see how the charts have then updated. And what I can do is if I use one tool here on a certain chart, all the charts and all the points are interconnected. So as I make selections on this chart in the bottom right, It updates the selection here to show me the points of interest. It updates the selection on the ternary plot. It updates the selection on the spectrum. And so suddenly you've got all these interconnected data points for X-ray spectrometry, telling you stuff about what's going on in the sample that was collected. And that, I think, is pretty cool. What you can then do if you are a science nerd is then, like, you know, click through elements of the periodic table. You can see where peaks are. So if I click on CL there, you can see how that corresponds to that peak there. So you know that there's some of that going on. If I keep on scanning, eventually I will. There you go. So obviously, because it's Mars, you've got iron, and so you can see the peaks that correspond there. And then whatever this one is, there's another one there somewhere. Oh, that one. And so you can see what was detected, and then you can run something called PyQuant. And so PyQuant was really the crux of how this platform worked. And under the hood, what used to happen was the data got sent to one researcher. The researcher would run this PyQuant stuff on their laptop, and it would take somewhere around 30 hours. And so we sat down and tried to figure out how best to distribute that PyQuant load across multiple nodes, because we're running this in AWS, and so we can figure out how to scale this thing up. And so by parallelizing chunks of PyQuant and the C code that underpinned it, we allowed that process to get distributed, and then also figure out how to, like, scale automatically. So under the hood, there's a whole bunch of Kubernetes stuff, and we could determine by how many elements you chose and how big a data set it was, how many nodes we would run optimally to get you the answer that you wanted in a time frame that was more suitable than like 30 hours. And so this got it down to like 5 or 10 minutes, depending on like the scan that you're doing. But, you know, basically it's doing a whole bunch of like crazy spectroscopy analysis for you, and then returns more detail about what you're looking at. And so you get these things called quant jobs. I don't know if I can select one of these. Access denied. Ooh, oh, that one I can. Oh, that one didn't complete successfully. But you get the idea. So you end up with all these quants. You get the logs that are coming out. I can then use it potentially, not with this one, but like, you know, you can select to use it inside of a workspace, and it'll tell you a whole bunch of stuff about the data that you're looking at. And this was cool. This allowed users to like sit and, you know, analyze the data that they were going through and really sort of dig into, you know, what they wanted to understand from a you know, spectroscopy perspective. But that was one user. So you've got one user who's sitting there doing their one thing with their data set. And so we wanted to be able to do two other things with it. We wanted users to be able to share their findings internally, so that if you're writing papers, you can go and, you know, show it to other people and get them to validate it for you. We also wanted for users who would then publish their paper to be able to link back to the platform, so that if people wanted to be able to reproduce the findings on a different platform using our software but somewhere else, they could go and find the build like number, all that type of stuff that it was used against, and then use that to go and rebuild the data sets. And so what we then did was build in like a massive bit of platform sharing and all that type of stuff, which I don't think I can show you because of the fact that I'm no longer a sort of super user or general user. I am now just Joe Public. But basically, you know, you could share all these regions of interest. You could share the quants, which obviously you can see here. You could do all sorts. And then, you know, you could display how all that worked in correlation. There you go, some more stuff. To like how this, like, you know, the findings you're doing. So this was cool. And so like users were able to then cite their research in a common platform that everyone had access to from a Mars Rover perspective, in a UI that was really tailored for what they wanted to do. It proved beyond doubt that, like, the old adage of, oh, just give me the data in an Excel spreadsheet, is actually not the best answer for a bunch of this stuff. And in reality, sitting down and talking to researchers and going, okay, what do you actually want, ends up being a more useful and fruitful outcome for everyone to have. And so, we went through a lot of this and a lot of pain where people were like, oh, just give me the Excel spreadsheet, just give me this, just give me that. And we kept on building stuff until we proved that they could suddenly do their research in an awful lot shorter time period than they could do before. And that was really the tipping point to getting everyone to use the platform and start really interacting with it in a way that allows for all these papers to then get published. Of course, one of the things that then did come up eventually was the fact that whilst people were able to do this stuff, like, there were limitations because you can only click through stuff to a certain degree. Like, you can't just keep on extending it because at the end of the day, it's a web interface. And again, this thing has changed a lot, but like over time we were like, okay, so like, how can we build something that allows users to access the data they want, see the data they want, interact with the data in a way that they want, whilst also giving them the flexibility to write code in an environment that keeps the constraints and the data lineage and the data history and the data versioning all in one place. And so Peter, my colleague on the project, ended up coming up with this sort of embedded Lua type setup. And so you can then plug in these modules into like any part of the process that, like, where you want to tweak the data. And so, like, you can create a module, you can bring the data in, and then you can release that module and then apply it to your data set. And so, like, here you go, push run, you've got a console output. And really, in the browser, this is like running this stuff, in real time. And again, that's a cool way for people to be able to sort of like take what they're doing, but extend it slightly, to allow for those sort of what if cases. And, sure, some of that stuff will turn into new features and functionality, but at least it stops them being blocked up and going to use something else in that time period. And so, in doing that, it really gave people the flexibility they're after. The other thing that we had were these element maps. And again, you can start to see, what the rock samples and the surfaces were made up of, again, in a joined up visualization that allows people to really interact with the data in a way that Excel does not allow you to do. So obviously I run a consultancy where we deal with a lot of this stuff. And so, I wanted to take you through, because one of the things that NASA did decree was, where possible, try and build stuff in the open, make that open source so we're not building in silos. And so data can get reused and platforms can get reused, and it drives that innovation. And so, like, one of the things that NASA did an awful lot of was like build things out privately and then release them once they were done and the funding had basically gone away. And so at that point, the stuff would be released, but it wouldn't see any updates and the thing would go and die a death because, you're just releasing it with no community built around it, nothing going on. And so, that would be the way. So what you've got here, github.com/Pixlise, is a number of repositories, and they all do different stuff. The only repository that wasn't public at the time that I was working on, and it still seems to be the case, is the infrastructure repo, because that obviously deals with the deployment into the old AWS environment. And so, like, how did we build this? Because it wasn't the norm. we built something that was a little bit different. And so when I joined the project, there was an awful lot of Python stuff, but Peter was based in Australia. I was based in the UK. There was a couple of people based in LA. And the thing was, we're doing, an awful lot of app development where there was data objects moving around between different platforms and that type of stuff. And it was originally written in Python. Now, I haven't got a problem with Python, and obviously an awful lot of data scientists use a lot of Python to build things. And so, we wanted to be cognizant of that, but we also wanted to build something that sort of made it easier to deploy things and manage our services. And so we tried a couple of different platforms, and in the end, we were sat there in LA one week in the middle of a hacking session. We're like, what are we going to write this in? And we both sort of sat there and went, well, I've heard some good stuff about Golang. And so that's sort of how we ended up settling on Golang. Now, the nice thing about writing an API in Golang is it compiles generally into a single binary. You can compile for different operating systems without having to run those operating systems. You can chuck that thing around into your desired container or target architecture very simply. And you get high performance code that's low level, it's designed for systems engineering and that type of stuff. Of course, it's evolved a bit since then, but it suited what we were trying to do. And so we built out this API layer as a proof of concept, and it's been rebuilt a few times, but the thing still remains the same, where you've got endpoints and you've got a whole bunch of Gorilla Muck stuff going on, but the actual API was super lightweight, easy to manage, maintain, all that type of stuff. And so we've got a whole bunch of Golang, which was definitely not the most common choice of data science platform development language when we were building this thing at JPL, and I suspect still isn't, but it works really well for what we need it to do, which is accept data, process the data, and then return the data to the UI. So what else did we do that was a bit different? Now, yesterday I did a live stream about Protobuf. And I had used Protobuf before, but this was sort of where I got really into using Protobuf, because we used it for basically all of the messaging that went backwards and forwards. And we used it for an awful lot of the spectroscopy data that was being built. So if I look at experiment.proto, inside of here is the Protobuf representation of the data that we were just looking at. You've got scan source, you've got image coordinates, you've got other context image info, basically everything that's in here. And what this allows you to do is package up one of these pieces of data and just hand it over to another process to do something with it. And the nice thing about Protobuf, as I said yesterday, is the fact that you can use these Protobuf files. So one of the things that this allowed us to do was write the API in Go and then not have to worry too much about what was going on in the front end or elsewhere, because we knew that as long as we could compile the Protobuf, the UI or whatever else, whatever process was going to consume it could definitely, consume it. And that was never going to be a problem. So we had all these Protobufs that then ended up, running the API. So again, if you want to have a look at job.proto, you've got job status, and inside of here, you've got a bunch of enums for different statuses of jobs and so on and so on. And this just means that you've got a very defined API layer, you've got a very defined data layer, and every UI and backend process can use it. And that's cool. So basically all we did was inside of the core project was add it as a submodule and then build off of the back of that. And this really allowed us to build this API layer out in a very defined, methodical fashion. in something that would allow us to run basically in any type of container, in any type of cloud without having to worry about it. The UI hasn't actually changed much since it started, like in terms of like technologies. It obviously has changed a lot in terms of interactions, the way that people work with it. But again, you've got data formats in here. And basically what you can do is use GenProto to like generate the TypeScript versions of the protobufs. On the Go side, we generate the Go versions. On the UI side, we create the TypeScript versions, and then we can leverage those inside of like, you know, whichever Angular object we want to. I don't know if this one has one or not, but like, you know, basically inside of here, we can then start to reference those models and, you know, really start to leverage the power of protobufs when we're moving data around a pretty complex platform with a lot of interconnected components and structures that we want to ensure remain functional when things change. And so that really allowed us to build all this stuff out. And so, like, you know, these days we have the core repo, the Pixlise UI repo, and the data formats. They're the three main repositories that this thing gets built against. We also have PyQuant, which is the stuff that under the hood does all the heavy lifting. Again, you've got the data formats. You've got a bunch of C++ that can then leverage those data formats. And so like this is why I wanted to show this having done yesterday's protobuf blog. This allows for the commonality between different parts of the platform to really, you know, show how that stuff would work at a platform level. And so, you know, this is the work that we went through to really prove to researchers that you don't necessarily have to, you know, just give me the row level data. You know, if you really put some thought into it and really, you know, asked yourself what you wanted out of an application, it is not Excel, or it is unlikely to be Excel. I won't say it's not Excel, but it is unlikely to be Excel. But people are so used to it that that's all they ever ask for. And then when they don't quite get what they ask for, the default is then like, you know, just give me the data and I'll chuck it into Excel, which again is sort of like, it's understandable why you would do that. But it also is the shortcut to means that then like you never build the thing that you should actually be building. And so, you know, that's why I'm a huge believer in, you know, building research environments that make sense, that work well for the researchers involved. It allows them to really, you know, tailor what they're getting to the use case that they have in hand. Because when governments and therefore taxpayers are like, you know, investing this cash, they should get something off the far end of it that is worth that money. And so like, I don't think a lot of the time that cash is worth it from I got an Excel spreadsheet, because where's the common good? Like, yes, you could share the Excel spreadsheet and the workings you did, that's great. But actually, if you could just build an app and allow other people to invest in that app, and if you've got, you know, an X-ray spectrometer, it doesn't have to be on a Mars rover to be able to use this piece of software. You just need to have a data format tool that generates a protobuf that matches the input source. And then all this just comes to life. And this is my point. Like, you know, there's so many different places and points in, you know, the work that you do where you could like leverage other people's work. And like, by sharing that code, sharing that goal, it really just allows people to invest in the wealth and deal like with the benefits of open source software. There you go. I hope this was interesting. I hope this is a little bit of insight into what we do from a research perspective, because there's an awful lot of research projects out there that could do with something like this. If you're interested in finding out more, feel free to leave a comment, get into my DMs, send me a message. We've got an awful lot of stuff going on, and sort of building research platforms is definitely one of them that's a lot of fun, and I am clearly quite passionate about. I hope you've had a good Friday. I hope you have a good rest of your day. And I will be back next week with some more ramblings from my green office. Goodbye for now.